Welcome everybody to the Integrability Journal Club. Today we are very happy to have Jakub Vošmera from ETH, and he will tell us about D-branes in ADS3 x S3 x T4 at k=1 and their holographic duals. Please, Jakub.
Okay, many thanks for the introduction and also for the invitation. I'm very happy to deliver this week's issue of the Journal Club. So my talk today will be based on a recent paper with my wonderful collaborators Matthias Gabriel and Rob Knighton. And yeah, as you can probably tell from the title of my talk, this is going to be all about ADS-CFT, which is a proposed strong duality between a theory of quantum gravity in D dimensions and a gauge theory in D-1 dimensions. So the questions which I'll be trying to address today is, although it is often said that this duality cannot be proved because it's a strong weak duality, so whenever one side is perturbatively tractable, the other is not. So I'll be trying to ask myself if nevertheless there can be a special setting where we can where both sides of the ADS-CFT can be thought of actually as tractable perturbative QFTs, and if and provided that this is true, whether we can actually find a setting where the Feynman diagrams on both sides of the duality would be actually exactly computable, and therefore this would give us a chance of actually proving the duality. And finally, let's be even more bold than that, whether we could actually investigate also non-perturbative objects on both sides and see whether they can be matched. So as for the first two questions, so this is going to be a review because these were already answered, starting with the paper by Lawrence Eberhard, Matthias Gabriel, and Francesco Pacumar in 2018. Whereas the third question, whether we can also do this for non-perturbative objects, this is something which we were trying to address in our recent paper with Matthias and Bob. So, so the rough outline of the talk is that after an introduction and motivation, I'll do a review of the story for the closed strings. So this will be a review of a closed string propagating on ADS3 x S3 x T4 at k=1 unit of NS flux. So this is exactly the setup where we can actually investigate exactly both sides of the ADS-CFT correspondence. And in the third part of my talk, I will actually try and put D-branes into the bulk of ADS3 and see whether they can be compared to something in the dual spacetime CFT, which in this case is of course the symmetric product orbifold. Let me first just quickly review a few things which we should know and love. And this is that the ADS-CFT correspondence states that that open string theory on a brane, or maybe better on a stack of branes, should be true to the closed string theory in the bulk. So the most famous example of this is of course the duality between the n=4 superangles in 4D and the type 2 superstring on ADS5 x S5. So let's see how this goes. we have a stack of D-branes on which the low energy effective field theory is exactly the n equal 4 superior mils. And then if we take n to be large in a certain way, such that this parameter lambda, which is called the toothed coupling, is kept constant, then this is true to type 2b superstring theory on ADS 5 cross 5, which is precisely the near horizon geometry for the spring configuration. So what does it mean for these theories to be true? So this is basically the essence of the holographic dictionary. So first of all, we should say that the on-shell co-string states in ADS should correspond to single trace operators in the CFT living on the boundary of ADS. Then we can take these on-shell co-string states and calculate the string sketching amplitudes, and these should correspond to the correlators in the dual CFT. And finally, the genius expansion of these amplitudes in ADS should then be compared to the corresponding loop expansion of these CFT correlators. So then if for large n we identify G as the co-string coupling constant with 1 over n, then this duality, or then this equation, which I just written down, where on the left-hand side is the genus expansion, on the right-hand side is the loop expansion in the dual CFT. So then this equation should hold order by order in GS. Sorry. So let's recall this relation which I've already displayed on one of the previous slides, and this is the toothed coupling. This can also be expressed as a ratio of the size of the ADS space and the string length, which I denote by ls. And this is basically the reason why this duality is called strong weak. So, for instance, I can choose to be in the supergravity regime where the string length is much less than the radius of the ADS. So then I see that my toothed coupling is much greater than 1. So that means that the conformal field theory on the boundary of the ADS is strongly coupled, and we shouldn't expect it to be tractable perturbatively. So, what people instead suggested is instead to look at the opposite regime, where the dual CFT is essentially free. So that corresponds to the string length being actually much greater than the radius of the ADS. So in this regime, the bulk is actually stringy. So we shouldn't expect it to be described by supergravity. I'm sorry. On the other hand, given that the dual CFT in this regime is essentially free, we should somehow expect that there should be a setting where also the bulk dual should have a simple description. But as I was saying, the supergravity description no longer applies here. So in order to look for such a setting, we'll be looking for a background which has an exact worksheet CFT description. Otherwise, we're just not able to say anything. All right. So this is something which was indeed realized 3 years ago in this paper by Eberhard, Gabadier, and Gopakumar, and this was in the context of the ADS3 CFT duality. So let me briefly go over this. So Now, instead of taking a stack of ND3 branes, I'm considering a superposition of N1 branes and K5 branes, where the 5 branes are wrapping this T4 as well as this S1. The 1 branes, they are wrapping just this S1. And then these then back react on the bulk to produce a near horizon geometry, which is exactly that of this ADS3 cross S3 cross T4. So moreover, these 1 branes, they can also be viewed as super Yang-Mills instanton which live within these 5 branes. So then I can immediately say that that the corresponding to the CFT should actually be the sigma model on the ADHM moduli space, where the singularities which are associated with zero size instantons are in general resolved by turning on various marginal deformations. So in this setup, I can look for particular values of parameters which give me an essentially free field theory living on the boundary of this IDS3. And this is exactly the point where the 1 branes being thought of as instantons within the 5 branes can actually be actually lifted away from the real volumes of these 5 branes, and this is exactly the symmetric Oberthorpe point. So in that case, the boundary CFT, the CFT which lives on the boundary of the ADS reduces exactly to the symmetric product Oberthorpe CFT, with the 4 torus being the seed theory for the symmetric Oberthorpe. So by symmetric Oberthorpe, I mean taking an n-fold tensor product of a seed theory of a seed CFT, which in this case is just this T4, and then modding out by the symmetric group which permutes the individual copies of the seed theory. And as it was shown by Abraham, Gabriel, and Gopakuma years ago, and as we will see in the review part of this talk, is that this symmetric product Oberthorpe CFT turns out to be exactly true to ADS3 cross S3 cross T4, where we pick on a k equal 1 of NS5 branes. So in other words, we are having an ADS3 cross S3 cross T4 with k equal 1 units of the NS-NS flux. So this theory turns out to have an exact Ricci description in the so-called hybrid formalism, which is originally due to Natan Berkowitz, Waffa, and Witten. And then the worksheet CFT can essentially be described in terms of the PSU 1,1/2 super WZ model at level k equal 1, where the currents of this model are denoted by this J, K, and the fermionic current S. And then the T4 factor becomes topologically twisted, plus I also have the ghosts. Now it is actually amusing that that this PSU 1,1/2 at level 1 has a pretty simple free field realization. So now you see that that a theory on the boundary, which is the symmetric product Oberthorpe, which is essentially free, is again dual to something which is essentially free, which is this PSU 1,1/2 at level 1, and in particular, this can be realized in terms of 4 symplectic bosons, which are denoted by psi plus minus and eta plus minus, and 4 real fermions, again denoted by psi plus minus and chi plus minus. So that means that since I'm dealing with free theories, I can compute spectra and correlators on both sides. So this was done in a number of recent papers by Andrade, Matthias Garpadio, Gopakumar, Bob Knighton, and other people. And this essentially provides a perturbative proof of the ADS-CFT correspondence in this particular case. So the main questions which I'll try and address in the second part of this talk, and which we have addressed in our recent paper, is if we can construct D-branes in the context of this setup. So this should essentially correspond to different boundary states in this PSU 1,1/2 because then whatever boundary states we consider for the T4 factor, they will essentially go on for a ride, as we'll see. And if provided that we can construct these, we can actually match them to some dual objects in the dual CFT, which is the symmetric protocol default. Whether they will be boundary states again or some other types of defects.
Can I ask a question now?
Yes.
I thought for k equal 1, the one single NS5 brane, there's no slot such that once you put the F1 string there, you would not get the ADS3 spacetime when you go to a near horizon.
Oh, okay. I'm not sure I'm not sure I've ever heard about such a statement.
Is there some?
You're claiming that for a single NS5 brane, I'm not getting ADS3 cross S3, or?
Yeah, I thought that in a single NS5, so typically there's a no slot along this NS5 brane. I mean, normally when you put like a multiple NS5 brane there, and then you construct a slot region, and you will find that it's a linear dilaton. And in order to cure this strong coupling, you put like a F1 string there, and then you go to a near horizon, it become ADS3. But I thought for just a single NS5 brane, there's no such. So I mean, in this paper, this Abhad and Gabdir and Gupal, do they say some thing about so in their paper they literally talk about like using one single NS5 brane can realize this ADS3.
Okay, yeah, I'm sorry, I'm not sure how I can answer this now. I've never really thought about. Yeah, I mean, yeah, I'm sorry. Yeah, I've been only thinking about this stuff like from purely worksheet point of view, where yeah, but of course, I can just do this, right? I can take this. Yeah.
Okay. Thanks.
Yeah, I'm sorry.
I think this is somehow. Yeah, sorry. I think this is somehow related to the fact that there are only continuous representation states in the case when you take the level to be 1. And in that case, usually continuous representations go to the boundary of ADS3. So in that case, I think they're not exploring really the bulk. So if I understood correctly, all these constructions of, Eberhard and company, is basically that the strings never reach the bulk of ADS3, but they keep staying at the boundary of ADS3. And that's the reason why they're only continuous representation in the tensionless regime.
Yeah.
Okay, I see.
I hope it helps.
Yeah. Good. Thanks.
Yeah.
Okay. Yeah. Thank you. Yeah. Thank you for the comment. All right. So okay. So now that brings us to the second part of the talk, and this is a more detailed review of what happens with the co-strings of ADS3 cross S3 cross T4. And indeed, in a moment, we will see that that the representations which are relevant for the closed string spectrum in the bulk are indeed the continuous representations of SL2R. So that will nicely connect to the comment which has just been made. So so let me first focus on this PSU 1,1/2 at level 1. So we can first have a look at the maximum bosonic subalgebra of this super WCW model. So this is just a direct sum of SL2R at level 1 and SU2 at level 1, where the currents are denoted by J and K respectively. Where of course the SL2R is describing my ADS3 factor, while the SU2 is giving me the S3 factor. Sorry. So more explicitly, I can write down, of course, the commutation relations of all these currents. But then, of course, I'll have the fermionic currents, which will then complete for me the super algebra. And in terms of representations of SL2R and SU2, these fermionic currents, they sit in two doublets. And then finally, I need to specify what the anti-commutator of this fermionic current is, and it is given by the following expressions in terms of Pauli matrices and these coefficients C, which are just essentially plus or minus 1. So as I was already hinting at, this algebra can be realized in terms of fields, namely in terms of two pairs of symplectic bosons and two pairs of complex fermions, which satisfy the following OPE, which look the same, but we of course need to remember that the symplectic bosons xi and eta, they are bosonic on the bridge sheet, whereas the fermions, they are fermionic, so they anti-commute. Then I can use these fields to form various bilinears, and these bilinears are exactly what is giving me the various currents. First of all, I can use these bilinears to form the spin-1 currents of the U1,1/2 at level 1. And then in order to obtain PSU, what I need to do is that I essentially need to take a coset with respect to this free boson Z, which if I compute its correlates, it's essentially central. So what I can do, I can set the modes of Z to be 0, and in the end, I also need to sum over various charges with respect to this other free boson, which I call Y. So this is giving me my PSU 1,1/2 at level 1 in terms of fields. Now, when I then want to go and construct various representations, it is also useful to remember that there is a non-trivial spectral fold isomorphism acting on PSU 1,1/2 at level 1, and implemented on the currents. It is given by the following expressions. Here, I mean, at this point, W can be any number, but when we will then go and construct the spectrum for the closed string propagating on ADS3, we will see that the W will need to be restricted to be an integer. So in terms of fields, the spectral for isomorphism acts in the following way on the symplectic bosons and free fermions. And finally, I can also find what it looks when it acts on the Drazor modes. So at k = 1, it turns out that only the so-called shortened supermultiplets are relevant, and this is what I'll denote by this F lambda. So here these can be specified in terms of representations of SL2R and SU2. So by this calligraphic CJ lambda, I denote the continuous representations of SL2R, where J is my spin. And we can see that it sits precisely at the edge of what would become the long string continuum. So then, of course, the quadratic casimir is parameterized in the usual way. And here the lambda can be taken from the interval from 0 to 1. And it is exactly giving me the fractional part of the J0 free eigenvalues, where J3 is the current of SL2R. And then by these bold numbers, K, I just denote the various multiplets with respect to SU2. So then the full affine representations are, of course, generated by acting with negative modes of the PSU 1,1/2 currents. And finally, in order to construct all representations which I will need, I should also consider these representations F lambda, where the spectral flow is applied. So if I then recall the form of the spectral flow isomorphism for the Virazoros, more specifically for L0, I can actually observe that these spectral flow representations, they are no longer in general affine highest weight modules. So the conformal weight actually becomes unbounded. But nevertheless, that doesn't stop me from constructing the corresponding characters. Here I display what I call the unspecialized characters. So apart from my usual modular parameter tau, I'm also including the chemical potential for the SL2R factor with its corresponding fugacity x. So there's a relation that e to the 2 pi I t is x, t is the chemical potential for SL2R, and x is the fugacity. And I can then look what the behavior of these characters under the modulo S transformation is. That is going to give me the modulo S matrix. And in order to construct the bulk spectrum of the corresponding WCFT, I then have to look at such combination of left and right moving characters so as to obtain a modular invariant bulk partition function. And in the end, I can fix this to give me the following spectrum. So I'm basically diagonally summing over all spectral full sectors and integrating over this fractional part of the J0 free eigenvalue. So this was just the PSU 1,1/2. So in order to obtain the full worldsheet partition function, I also need to add the ghost and the 4 torus contribution into the game. And if I do that, I can end up with the following expression. And this is actually giving me a first hint of a more general story. Namely, I see that the worldsheet modulus tau becomes delta function localized exactly at such values where the worldsheet homomorphically covers the space-time, which is described by this parameter t. So what I in fact want to do when I want to compare to the spectrum of the boundary CFT, I want to consider the on-shell worldsheet partition function, and that should give me exactly the single particle partition function of whatever the dual worldsheet CFT is. The dual spacetime CFT is. So in order to do that, I can take this above expression. Take this above expression for the worldsheet partition function, and impose the mass shell condition together with the level matching. And after I do that, I indeed recover the following expression, which you may recognize as the single particle partition function of the symmetric product of default with the T4 as the seed theory. And at the same time, I can notice that the spectral fold sectors in ADS3, which describe ghost strings which rewind W times around the center of ADS3, exactly corresponds to the W cycle twisted states in the symmetric product orbit. So that was the comparison at of the partition function. In general, I would like to do this for all correlation functions. So again, the statement here is that I want to take an amplitude of the ghost string theory in the bulk, and I want to compare it to some correlator for the CFT which lives on the boundary. So I'm considering amplitudes of on-shell vertex operators in the bulk, which are now no longer parameterized only by a point where they are inserted on the grid sheet, but also by this point X where they are inserted on the boundary cylinder, and the corresponding endpoint G loop amplitude can then be expressed in the following way. All of this is done in the hybrid formalism. So there it turns out that apart from inserting the on-shell vertex operators, I also need to insert these fields W, which can be thought of in a way as a spectral changing operators in the hybrid formalism. And then, in order to evaluate such a correlator and then the corresponding amplitude, it is useful to collect various OPEs and relations for the symplectic bosons and the on-shell vertex operators. So the strategy, which turns out to be very useful here, is that before we actually calculate the correlator which we want, we define the following homomorphic functions, which we call as omega plus minus. So these look pretty much the same as the correlator which I want to compute, but I have this additional insertion of the symplectic boson xi plus minus z. And using the OPEs which I collected above here, I can actually show that these functions omega plus minus have the following properties. They have poles of order wi plus 1 over 2 at z equals I. They also have simple zeros precisely at the points where the picture changing operators are inserted, and the following combinations of omega is omega minus plus xi omega plus has zeros of order wi minus 1 over 2 at z equal to zi. And it turns out that these properties alone are enough to fix that if I define a function capital gamma as a ratio of minus omega minus over omega plus, then this is exactly the homomorphic covering map, which takes me from the Riemann surface on which I'm computing the amplitude, that is an unpunctured Riemann surface at genus G, to the boundary of the ADS3, which is just a two-sphere. So this is true provided that such a covering map actually exists. So of course there is a homomoduli space of these Riemann surfaces sigma, over which I eventually want to integrate if I want to calculate my amplitude, and such a homomorphic covering map actually doesn't exist everywhere in this moduli space NGN, but only at isolated points. So at points where this gamma does not exist, something needs to go wrong with our construction, and the thing which goes wrong is actually that omega plus vanishes. So this is this thing which appeared in the denominator of the definition of capital gamma. So and this vanishing of omega plus then implies actually the vanishing of the amplitude which we originally wanted to compute. So this leads to the following statement that for the tensionless, for this k equal 1 ADS3 cross S3 across D4, the integral over the mgn, which appears in the calculation of the amplitude, actually delta function localizes at the points in ngn where the homomorphic covering map from the sigma gn to the 2 sphere exists. So so this can be immediately compared to the so-called Ullmann-Matter way of calculating the sphere correlators of W cycle twisted states in the symmetric product orbifold, and this essentially is what gives me a perturbative proof of this particular instance of ADS-CFT duality. So I think now I spent about 35 minutes of my talk, so perhaps that would be a natural point where to make a break. Would you agree? It's not exactly 40 minutes, but in the second part, I would do this final part of the talk, if it is okay.
Yeah, of course. Sounds
okay.
Good. Okay, so yeah, we'll take a break of 10-15 minutes. So people should feel free to ask questions and discuss informally.
Yeah. So.
Okay, yeah, please.
We can continue, right?
Yeah, please.
Okay, so up to now we've been reviewing reviewing the known results on what happens in the bulk of ADS3 in terms of purely cold strings. So in the final part of my talk, I would like to try and address if we can say something when we put D-branes in ADS3, and if these can be compared to some corresponding objects in the boundary CFT, which is a symmetric product orbifold. So before I actually start doing this, so let me include one sort of slide on the description of D-branes in terms of boundary states. So from the point of view of the worldsheet approach to string theory, D-branes can be specified by giving one-point function or one-point amplitudes of the bulk fields, and these can be nicely packaged into objects which we call the boundary states. Now these boundary states they are generally expanded in a basis of the so-called Ishibashi states. Where the Ishibashi states are essentially given by spinless primaries of the bulk CFT describing ghost string theory. So this is exactly this expansion here. Sorry, where the coefficients of this expansion, these BI, are exactly proportional to these one-point amplitudes of the co-string fields Vi in the presence of the given D-brane. So these boundary states, there are bulk CFT states which preserve exactly 1/2 of the bulk chiral symmetry algebra, and this is expressed by means of these what are called Gluing or Ishibashi conditions. But then of course there are strict consistency conditions on what these boundary state coefficients Bi can be, and these go by the name of the Cardieu-Levelin Soling relations. So as an example, I'm going to give you a genus 1 condition, which is the famous Cardi's condition, and this can be basically described as an open-closed duality. So I can take 2 D-branes or 2 boundary states, and I can consider a co-string which is propagating between these 2 D-branes. So this is exactly this is exactly the point of this diagram. I have a closed string propagating in a tree channel between two D-branes, and this can be calculated. The corresponding amplitude can be calculated by taking two boundary states, A and B, and sandwiching a closed string propagator between them, which is this object. But now this can be also looked at from a sort of orthogonal point of view, from an orthogonal channel, which is the open string channel, where I have an open string stretched between two D-branes and propagating in a loop. So this is this situation, and then the statement is that of course that these two need to be that these two ways of computing the amplitude need to give the same result, and this gives me the Cardy's condition, which basically says that an overlap of two boundary states with this propagator needs to be giving me the open string partition function, which can be written as a trace of q to the L naught over the Hilbert space of the states with my open string, which is the Hilbert space of the corresponding boundary conformal field theory. So this much for a short review of boundary states, and now let's go straight back to our ADS 3 cross S3 cross D4 story. So first of all, I would like to recall a simple fact about the D-branes in WZW models, or boundary states in WZW models, and that is that their corresponding word volumes can be viewed geometrically as the conjugacy classes of the corresponding group manifold. In the case of the SL2R WZW model, which precisely describes the ADS3 factor, at k equal 1, it turns out that there are two inequivalent ways of choosing maximally symmetric cooling conditions on the boundary states, and geometrically, the first one of them is giving me the word volumes, which are essentially hyperbolic two planes at constant time slices. So here we call them spherical branes, not hyperbolic branes. And the reason for that is that if instead we go to Euclidean ADS3, then the boundary states, which are given by exactly the same cooling conditions, they will give branes with word volumes which are spheres and not hyperbolic two planes. But unfortunately, the name sort of got stuck in the literature, so we will also call them spherical branes in the case of Lorentzian ADS3. And the other sort of conjugacy class, which I can obtain, which is not equivalent to the previous one, is the one which is giving me the ADS2 submanifolds inside my ADS3. So the corresponding branes will be called ADS2 branes. Sorry. Yeah. So this is exactly what I've been describing now. Again, sorry. Of course, this fixes me the corresponding boundary condition on the open strings in the ADS3 factor. Then, of course, I have the S3 factor, which is described by the SU2 Wessel-Witten model at level 1. So there, the corresponding conjugacy classes are just the S2 submanifolds. And by the way, I should also mention the fact that, or emphasize the fact that we are at k equal 1. So what I've been telling you up to now, that D-branes and WZW models are wrapping the conjugacy classes, is strictly speaking true in the limit where the level k goes to infinity. At any finite level, the corresponding word volumes will not be exactly sharply defined along these conjugacy classes, but will be somewhat fuzzy. And at k equal 1, where everything is very stringy, and the sizes of my spaces, be it the S3 factor or the ADS3 factor, are of the order of the string length. Then in these cases, the geometrical picture of the corresponding D-branes will be somewhat smeared. So this is my ADS3 cross S3. So the D-branes for this will be described by boundary states in this PSU 1,1/2 model. Then, of course, in order to specify a boundary state for a full brane in the string theoretic setup, I also need to specify the corresponding boundary state for the D4 factor. So this I will take just to be an arbitrary brane inside this D4, which preserves the maximum possible amount of supersymmetry. So that is exactly 1/2. So typically this will be just some DP brane like a D0 or D1, D2, D4, right? And then of course I need to supplement all of this by the corresponding boundary state for the ghost, which will be just universal, and I'll be essentially not interested into any details of this. So so let me have a more detailed look at these boundary states for the PSU 1,1/2, starting with the spherical D-branes. So for the SL2R currents, the corresponding boundary states, the corresponding Ishibashi states need to satisfy the following gluing conditions. And if you then go back and have a look at the relations for the spectral isomorphism acting on these J currents, you can actually conclude that these gluing conditions are compatible with spectral flow. So starting with an Ishibashi state in the 0 spectrally fold sector, I can define Ishibashi states in all other W spectrally fold sectors simply by acting with the isomorphism on the Ishibashi states for W equals 0. And the same way, the gluing conditions are also compatible with all values of lambda, as you can convince yourself by setting n to be equal to 0. Then the full boundary states should be expanded as a linear combination of these Ishibashi states. And the way to do this the way to fix these coefficients is, of course, to require consistency when we calculate overlaps and go to the open string channel. So when we then go to the open string channel, we should be able to see that we are getting positive integer multiplicities, because the corresponding overlap of the boundary states in the open string channel should be interpretable as a partition function. And indeed, with this particular choice of the boundary state coefficients over here, when we then go and compute the corresponding self-overlaps of the boundary states, we find that in the open string channel, we're actually getting just a single PSU 1,1/2 representation, which is this essential vacuum representation f 1/2. So yeah, this is actually something which you should have expected. So these boundary states, or these gluing conditions, they are compatible with all states in theory. So that means that these should really be something like instantons for the usual free field boundary states, and correspondingly I should obtain an open string spectrum which is very short and which essentially just contains the vacuum representation, which is exactly what I'm getting. Then these boundary states, they are labeled by its parameters, parameter capital W and capital lambda. The capital W essentially, well, it is an integer and provides shift along the ADS3 time direction, whereas this lambda it essentially turns on the Wilson line along the angular direction of the ADS3 cylinder, where these spherical D-branes satisfy Neumann boundary conditions, so it makes sense that I can turn on a Wilson line there. So let me just briefly go over the analogous setup for the ADS2 branes. So there I have slightly different going conditions for the SL2 occurrence. So if you compare with the previous slides, instead of this minus here, I have a plus here, and I'm going J plus with J plus and J minus with J minus, whereas here I was going J plus with J minus and J minus with J plus. So in this case, it turns out that these going conditions, they are compatible only with the value lambda equal to 0 or half, and they are not compatible at all with respect to full isomorphism. So there are essentially only two Ishibashi states, which I can use to construct my boundary states, and these are labeled by W0 and lambda equal to 0 and a half, and can be expressed in the following way. So here the boundary states for the ADS2 branes, they are now labeled by this parameter theta, which is an analog of this parameter capital W for the spherical branes, but now we are not getting integer shifts along the time direction of the ADS3, but along the angular direction, and these integer shifts are just basically by pi. So the different values of theta, which is just 0 or 1, essentially correspond to having an ADS2 brane or an ADS2 anti-brane. Then I can do a similar exercise as I did for the spherical D-branes. I can verify that this particular choice of boundary state coefficient is giving me a consistent open string spectrum, and indeed it does. And I can observe that now there is a selection rule on the possible values of spectral flow which can appear in the open string spectrum, and which now depends whether I'm taking an overlap for brane and brane, or anti-brane and anti-brane, or if I'm taking a relative overlap between a brane and an anti-brane. So depending on that, I'm getting either even or odd values of W in my open string spectrum. So this was the construction of boundary states for this ADS3 cross S3 cross T4 at k equal 1. But now, of course, I would like to see whether these can be related to something known in the symmetric product of default. So let's see about that. As I was already commenting on, the total virtue boundary state is formed by taking a product of the PS1,2 boundary state, which is this object here, then the torus boundary state, which I label by some u, and the ghost boundary state, and the quantity which I would now to compute and to compare something with in the symmetric product of default is exactly the cylinder or the annulus amplitude for a closed string propagating between two spherical branes in the bulk of ADS3. So this is nicely depicted on this figure. I'm considering two spherical D-branes, which are separated by a finite distance along the time direction of the ADS3, and I'm considering a closed string, which is depicted by this blue worksheet, which is propagating between these two spherical D-branes. And in order to calculate an amplitude for this closed string being radiated by one of these spherical D-branes and absorbed by the other, what I need to do, I of course need to calculate the following overlap of the boundary states. So in the overlap, I not only have the closed string propagator here, I mean the worksheet closed string propagator here, but also the space-time worksheet propagator here, because as you might remember, J3 plus J3 bar is a generator of time translation on the boundary cylinder of my ADS3. And here I'm also using the cooling condition satisfied by the spherical D-branes. So I'm basically identifying J3 with J3 bar. So I'm just writing J3. And then in order to make this overlap into a non-string theory amplitude, I also need to integrate over the worksheet modules, which is essentially just the length denoted here by tau. So let's just quickly go over this calculation. So after a couple of steps, I can actually arrive at this expression for the anomalous amplitude, and again I'm see that some delta functions are appearing here. So in particular, this delta function enforces the following identification between the worksheet modules T between the worksheet modules tau and this parameter T, which was the shift of the spherical D-branes along the time direction of ADS3. So so this can be nicely interpreted again in terms of the covering maps, and in particular, I can recognize that these delta functions, which appear in the calculation of the cylinder amplitude, actually enforce localization of the worksheet modules at those precise values that the holomorphic covering maps from the worksheet cylinder, that is the blue thing here, to the space-time cylinder, that is this gray region on the boundary of the ADS3, exist. So this already gives me a strong hint on what the corresponding objects on the boundary can be. So here I can see from this picture that these spherical D-branes they create something which looks like some sort of a defect on the boundary cylinder of the ADS3. So the question is, what type of defect is this? Is this a topological defect, or is this a factorizing defect that's essentially again a boundary state? And this kind of calculation is telling me that when I consider a cylinder amplitude on the worksheet, what I'm essentially getting back is something which is going to look a lot like a cylinder amplitude, like a cylinder amplitude of the space-time CFT. And indeed, I can actually do the following steps. So in order to match with something in the dual CFT, it turns out to be convenient to do two things. So up to now, instead of the usual thing when we fix the number capital N of the F strings, which propagate between these two spherical branes, I'm going to fix a chemical potential for this N, which I'll call sigma, and this will essentially correspond to going to the ground canonical ensemble for such amplitudes. And then finally, in order to actually be consistent, I also need to go back and realize what I'm actually doing here. I'm actually computing a string path integral, and this is actually not the only contribution to the string path integral in this case, and I also need to include a contribution which comes from two disconnected disks, where essentially the costring here, as it is radiated by one of these D-branes, it disappears at some point, and then it reappears at some other point and gets reabsorbed by the other brane. And this is something which eventually gives me the correct ground state shift for the space-time CFT. And finally, after doing these steps, I obtain the corresponding cylinder amplitude in the ground canonical ensemble, and it is given by this expression. So it is given in terms of this overlap here, where this U and V T4 are, remember, the boundary states for the T4 factor. So this is nothing but a cylinder overlap for the four torus boundary states. So So let's see if there is an object in the symmetric product orbifold which gives me the same expression for the cylinder correlator in the ground canonical ensemble. And it turns out that these are the so-called maximal fractional boundary states. So the idea here is to start with a boundary state in the n-fold tensor product of the seed theory, which is my floaters, where in each of the copies the boundary state is endowed with the same label, which I call U. Now, in order to go to the symmetric, in order to construct the corresponding symmetric orbifold boundary state, I just follow the usual prescription for doing so in non-abelian orbifolds. That is, since this boundary state in the covering theory in the n-fold tensor product theory is invariant under the action of the orbifold group, I know that this will need to couple maximally to the twisted sectors in the symmetric product orbifold, and I can just write down the most natural expression for these boundary states, which was independently derived by this group, and check whether it gives me consistent overlaps after going to the open string channel, and indeed it does. So let me just briefly describe various objects which go into this expression. So here, these boundary states UT4 with gamma r in the exponent are the following objects. So I'm summing here over all permutations in Sn, which I write as a product of disjoint cycles, where gamma 1, gamma 2 are exactly these disjoint cycles. And then these sort of boundary states, U, T4, gamma R, have exactly the same boundary state coefficients as the original boundary state UT4, but now they are constructed on top of vacua which are twisted by the cycle gamma R. And here also rho labels the different representations of Sn, and chi is the corresponding character of Sn. So now it turns out, then of course I can go and I can compute the overlap and go to the open string channel and see that I'm going to get integer multiplicities. And what's more, if I specialize to rho being the identity representation or the trivial representation, and calculate the corresponding overlap of these maximal fractional boundary states in the ground canonical ensemble, which I define in the following way, what I obtain after a couple of manipulations is exactly this ZUBPT, which was what I called the ground canonical version of the cylinder amplitude computed from the bulk. So this gives me a very strong hint that the spherical D-branes for the tensionless string in ADS3 cross S3 cross T4 should be identified with maximal refraction boundary states in the symmetric product orbifold. So in order to give further arguments for this identification, let me just quickly go over the disk amplitudes. So what we've done now up to now was just a cylinder amplitude. So let's see how this goes for disk amplitudes in the bulk. So again, this goes pretty analogously to what was happening to the amplitudes for Riemann surfaces without the boundary. Now I have a disk, which is a Riemann surface with a boundary, and an arbitrary number of punctures. So this is the let's say the kernel of the amplitude which I want to compute. It's just a correlator in the rigid CFT. And in order to calculate such a correlator, I can just use the usual trick which people use, and that is instead of calculating a correlator on an upper half plane, I can calculate this as a correlator on the full Riemann sphere, where I put suitable mirror charges on the over half plane, right? Where the operators which are inserted, the anti-homomorphic images of the insertions in the upper half plane are determined by the particle boundary condition which I'm imposing along the real line. So then I can use quite an analogous strategy to what was done in the bulk, and given the cooling conditions which are satisfied by the symplectic bosons on the spherical D-branes, I can define the following quantities: capital plus or minus omega, capital omega plus or minus, which should be thought of as an analog of this lowercase omega plus or minus, which I had for the closed strings, and I can see that that again they have the following properties, which essentially guarantee that the quantitative capital gamma, which I define as minus ratio of capital omega minus and omega plus, is exactly the homomorphic covering map, which takes me from an unpunctured upper half plane to an unpunctured disk, if it exists. And if it does not exist, then omega plus needs to be 0, which in turn again gives me that the amplitude vanishes, and this again gives me that the amplitude is essentially localized at those points in the moduli space where this homomorphic covering map is there, and this in turn should be actually identified with the genus 0 contribution to the corresponding Lonin-Mater method for computing disk correlators of maximal refraction brains with purely bulk insertions. So that brings me to my last slide. In this talk, we've seen that there exists a setup in the three-dimensional version of the ADS CFT duality where both sides can be exactly computed, and that we can actually prove that the correspondence is valid order by order in the expansion in the closed string coupling. So these 2 points, this was just a review of the results which were already there. And we have also seen that we are able to match at least one example of a non-perturbative vacuum on both sides, namely the spherical D-branes in ADS3 cross S3 cross T4, were identified with the maximal refraction of boundary states in the symmetric product orbifold. So now we can take these spherical branes and try and use them, because they do, if you remember, those were instantonic. We can try and use them to compute the instanton corrections to the closed string sketching amplitudes in ADS3. So now after a beautiful series of papers by Ashoksan, we know that we know how to do this using string field theory and other very cheap methods. We can also, yeah. So as you can probably tell from the last part of my talk, we don't really have a precise idea what happens for the ADS2 branes, to what sort of quantities they correspond in the symmetric product orbifold. And of course, apart from the spherical and the ADS2 branes, there can be all sorts of other branes in the bulk of ADS3. So I've only been focusing on boundary states which are, let's say, maximally symmetric with respect to which are maximally symmetric with respect to the Cairo algebra of my WCW model, which was PSU1,2. But of course, there can be D-branes for boundary states which are less symmetric and which essentially just preserve the total Virasoro stress energy tensor. We can also go and not only consider boundary states and worksheets with boundaries, but also non-oriented worksheets. That is oriented faults and cross-cap states, and see whether the correspondence also can be extended to such a case. So this is a work in progress with Matthias and Bob. And then of course we can try and do an analogous construction in the ADS5 S5 setup, which is being developed by Matthias Cabello and Rajesh Gopakumar, and which started with their paper earlier this year. And finally, it would be of course very interesting to try and deform away from the K=1 case and see whether we have also something to say about D-branes and other non-perturbative objects for other values of the parameters. Okay, that's all from me. Thank you.
Okay, great. Let's thanks Jakub for the very interesting talk. And now we have time for questions.
One question I have is, that as you said at the beginning, your third part is that this kind of technology worked for, I mean, is strictly speaking true when you have large K. I mean, the level doesn't look quite.
No. Okay, this is okay. If I said this, this is not what I meant to say.
Oh, no, maybe I misunderstood. No problem, misunderstood.
No,
this is very likely.
What I meant to say is that the geometrical picture works for large K.
I see. Okay.
I mean, we're not relying on any sort of geometrical arguments. We're just doing pure algebraic consideration with the exact formulation of our worksheet CFD. So I mean, all computations which we are doing are in terms of the boundary state, which of course hold for all values of K. I mean, the thing which only holds at large K is strictly speaking the geometrical interpretation in terms of the conjugacy classes, right? But we don't rely on this. We do not do any sort of semi-classical calculations which could be done perhaps for large K. We don't do this.
Okay, no, thank you. I misunderstood for sure.
Okay.
I did.
No problem.
Thank you again.
Okay, any other questions? Comments? Okay, so then let's thanks Jakub again. And I think we can stop the official part.